Who's a grad student here at UC Berkeley. Tell us about computational advantage from Gibbs states.
Thank you very much. Great, so today I'll be talking about our upcoming work titled Quantum Advantage with Constant Temperature Gibbs Sampling. This is joint work with wonderful collaborators, Anthony and Thiago. So broadly speaking, our work is about the complexity of Gibbs sampling. And in thermal equilibrium, quantum many-body systems are expected to lie in their Gibbs state described. The process in which a thermal system converges to its Gibbs state is known as thermalization. And it defines a very natural, physically inspired model of computation in which one couples the system of interest to a thermal bath at some fixed temperature, and you simply just wait for it to thermalize, eventually converging to the Gibbs state. So the dynamics of this process is driven by what's known as a Lindbladian, or thermal Lindbladian, or Davies generator. And the question we'd like to study in this context is there a meaningful notion of quantum advantage in this dissipative model of computation? So there are two regimes which arguably make this question challenging. The first one is that at high enough temperatures, one really expects Gibbs states to be classical objects. And at low enough temperatures, this producing the Gibbs state is expected to be hard in general for quantum computers. In fact, NP hard via the classical PCP theorem. So somehow searching for Hamiltonians whose Gibbs states are both easy to produce on quantum computers and yet hard to sample from on classical computers are something of a sweet spot in the middle. So with that, I can start to formalize the task we're going to study. And the task is, given a local Hamiltonian, specified by its local interactions, and some inverse temperature beta, we consider the task of approximately sampling from the distribution given by measuring the Gibbs state, in particular in the computational basis. And our main result says that there's a family of n-qubit nearly local, namely log n local, Hamiltonians, and some constant inverse temperature, which is both rapidly thermalizing, or if you prefer, efficiently sampleable on a quantum computer, and yet classically intractable under standard complexity theoretic assumptions which arise in the literature of quantum advantage, which I'll get to describing shortly. Is this clear? Any questions before I move on?
So log locality doesn't affect thermalization, right? I guess they probably depend on locality.
Yeah. The parameters will be a bit more precise shortly. Great. So
Intractable, you mean it's hard to sample from it classically?
Yeah. Great. So to give a rough outline of our approach, the basic premise will be to engineer some family of local Hamiltonians, which is classically intractable by embedding some hard quantum computation into its Gibbs state. And this already poses the key challenge because in a sense, Gibbs states are understood to be thermally noisy versions of the ground state, and yet typical ways to embed circuits or quantum computations into Hamiltonians do so by embedding it into their ground states. So whatever embedding we choose will have to be in some form noise robust. And simultaneously, we'd like our system to be rapidly thermalizing. So in other words, we'd like to produce it as fast as possible on a quantum computer. And what that entails is a bound on a certain mixing time for some thermalization process. And in general, this is understood to be quite challenging, even on very simple commuting systems. So with that said, the real question is, what do our Hamiltonians look like? And so they're the well-known parent Hamiltonians of quantum circuits, which have found other applications in quantum learning theory and quantum complexity theory. To define them, we start with a very simple Hamiltonian, which is a sum of z's. And then we consider the family which is conjugating the sum of z's by a low-depth circuit. These Hamiltonians have a number of nice and quite simple properties. They're local, where the locality is a function of the depth of the circuit. They're commuting and they have integer spectra, which are consequences of the original non-interacting system. And crucially, the ground state is the output of the circuit. What is slightly non-trivial, however, is that their Gibbs states actually resemble a noisy version of the circuit. That's the name I found in the literature.
But it's not like you have a state of which you're building a Hamiltonian like a unique ground state or something. It's just.
Zero state and you apply the circuit.
Oh, sorry, I missed that part. That was not my fault. Apologies.
Great. So the Gibbs state resembles a noisy version of the circuit under input noise. And to see this, it's actually a quite illustrative two-line calculation where we begin by writing out the Gibbs state of the non-interacting Hamiltonian as a tensor product state, and in particular, a classical tensor product state. So it looks like the output of the depolarizing channel, which I placed in the top right-hand corner. And then it really just suffices to conjugate both sides by the circuit using the convenient identity again in the top right-hand corner. So what's nice about this description is that it already kind of gives us a framework for embedding hard computations into constant temperature Gibbs states. It really just suffices to find a quantum computation, which is hard to sample from under input noise. Unfortunately, this input noise model is a little non-standard in the broader context of quantum error correction. However, a very elegant work by Bremner, Montanaro, and Shepard studied it in 2016, where they have this very convenient or very illustrative message, which essentially says that many shallow circuits, quantum shallow circuits, which are classically hard to simulate in the ideal case, they actually become simulatable under input noise. So somehow, however we approach this problem, we're going to need some form of error resilience or fault tolerance, which justifies the earlier statement. With that said, I can now get to the outline of, yeah.
So did BMS prove it for random circuits or something? Is that why?
Random IQP circuits, which I'll discuss shortly.
Okay.
Yeah.
So why does their construction for fault tolerance not solve your problem already?
That is very good. It at a higher locality, something like that would work.
Okay. So you're reducing the locality of that.
Yeah. Any other questions? So with that, I can get to the outline of the rest of the talk. It will be divided roughly into two parts. Part one will be about designing Gibbs sampling algorithms for this family of parent Hamiltonians. And what that entails roughly is bound on a mixing time for a carefully engineered Lindbladian via arguably kind of clever light cone arguments. And part two will be about complexity theory, and in particular about designing circuits or fault-tolerant circuits which are hard to sample from under input noise. To dive in, the main result of part one is on a Gibbs sampling algorithm, which says that for every parent Hamiltonian of some quantum circuit, there's a quantum algorithm to prepare its Gibbs state in depth, which is linear in system size and exponential in the locality.
So why don't you sample the initial beta minus beta non-interacting qubits and just apply the circuit?
Yeah, this is a technicality that I might have time to go into later. It's kind of unclear whether you can recover the circuit from the Hamiltonian terms. In fact, we believe that to not be possible. That is not rigorous.
So what's the Hamiltonian?
The Hamiltonian term, yeah. This is very different than perhaps the Feynman-Kitaev mapping, where the unitaries are written out explicitly. Great. So,
It's kind of a promise problem, a promise that it's constructed from unrelated events.
yeah. Great. With that said, our algorithm is based on a two-step approach. The step one will be on designing a family of Davies generators whose transitions or jump operators are carefully engineered to resemble the connectivity of the underlying circuit. And then we'll subsequently present a proof that it actually mixes rapidly by means of what's known as a log Sobolev inequality. So in other words, this gives us this log n bound on the mixing time. So this is already, in a sense, a thermal algorithm in the dissipative model of computation. But if you prefer, step 2 is on the simulation of this mixing process on a quantum computer, using some of Anthony's prior work with Castoriano, Brandão, and Gillian. And this comes at the linear cost per time step, which is where the linear dependence comes from. Great. So to dive in with some background, a thermal Lambdian, or a Davies generator, is specified by 2 ingredients. The first ingredient is a set of jump operators, which kind of play the role of transitions in MCMC, for instance. And for the purposes of our construction, we'll simply consider local Pauli operators, whose support is the same as the light cone of each qubit. So to be more clear, this is just the same support as the Hamiltonian terms. That's what I meant by underlying connectivity earlier. And the second ingredient is a set of transition weights, which is where the temperature dependence comes into play. In our talk, we'll just think about the kind of standard Glauber dynamics weight. Put together, they define a Davies generator, which is the super operator, where the linear operators a sub mu are the jump operators projected down into the frequency basis. So if this is the first time seeing this, this might seem a little scary, but fortunately, we won't really need too much of its structure for this talk. Great. So with that said, this Lambdian defines an equation of motion, where the evolution of the density matrix is determined by this exponential map. And under rather modest constraints, this Davies generator satisfies the condition known as detailed balance, which for the purposes of this talk just means that the evolution fixes the Gibbs state. So we know now that, that this process converges to the Gibbs state. The real question that remains is, how long does it take? To start to quantify the rate of convergence of this process, we need the concept of a mixing time, which is just the smallest time for which the distance between any 2 states halves. Now, there are 2 general purpose methods to bounding the mixing time of Lambdian evolution. The first of which is a bound on its spectral gap, which results in this n over lambda, where lambda is the gap, dependence on the mixing time, or upper bound for the mixing time. However, what's slightly inconvenient is that this bound inherently comes at a polynomial overhead in n in the system size. A much more fine-grained analysis is known as a log Sobolev bound, or log Sobolev inequality. Yeah, shoot.
Would you be unhappy if the mixing time was shown to be polynomial rather than rapid? Like
for the purposes of advantage, that's completely fine. But just generically speaking, we'd like to produce these Gibbs states as fast as possible. And ideally, since we already know that there is a circuit that would generate the dynamics and is short, we might as well hope for a simulation which is short as well. Yeah.
Don't you also need to prove that the Gibbs state is a unique fixed point?
That's a very good point. In general, yes, if it were a generic Lambdian dynamics, but for Davies generators, these things kind of collapse.
So it's unique. Like
yeah, but there's no control over the gap, at least a priori. Anything else? Great. So a log Sobolev bound, in a sense, it quantifies the rate of decay of the relative entropy of the time-evolved Gibbs state to the the time-evolved density matrix to the desired Gibbs state, where for convenience, this is the relative entropy, the quantum relative entropy. So this rate of decay, it's always negative, or actually non-positive. But if you could actually prove that it's bounded below 0 by itself, that's what would constitute a log Sobolev bound, where alpha is the log Sobolev constant. So this directly implies an exponential decay of the relative entropy itself, which under standard entropic manipulations implies a polylog bound on the mixing time, which is a phenomenon known as rapid mixing. Now that we've set up the goal, I wanted to start with a very simple example in fact, the simplest Hamiltonian in the family, which returns to the case where there were no circuit at all, and we're just looking at a sum of z's, where the Gibbs state is a tensor product. So if we were to plug in this Hamiltonian through our framework, the jump operators will just be single qubit Pauli operators, and the Lagrangian itself is non-interacting. So this is arguably the simplest Lagrangian you could possibly write down. And I'd like to convince you guys that its analysis is just based on looking at how these operators L single act on 2x2 matrices, which you can just write down explicitly. I won't bore you guys with the details, but we claim that this system, this non-interacting system, satisfies a log Sobolev bound with a constant which only depends on the temperature. So our goal in the rest of the analysis is to somehow inherit this fast mixing of the non-interacting case for the case with a circuit. And to do so, the key idea is what we refer to as a concavity claim, which roughly speaking says that if we were to look at our Lagrangian in a rotated basis by the circuit itself, it actually looks like a convex combination of Lagrangians, one of which is the system we just understood, and the other one, L rest, might be arbitrarily complicated. But at least we know that they both have the same fixed point. And moreover, the convex combination constant just depends on the locality, not the system size. Yes, standard but slightly technical entropic manipulations turns out that convexity or concavity is all you need. This actually gives us a log Sobolev bound for original Lagrangian L, but with a constant that only depends on the original non-interacting constant and the convex combination constant.
And you just need poly jumps and stuff. Like, local jumps can be polys and stuff.
So how we get this concavity claim is where the jump operators come into play. But this statement is, this concavity argument works regardless of the jump operators.
And it depends on the depth of the circuit.
Yes, yeah. Good. So in the rest of this first section, I kind of wanted to give a sketch for how we go by proving this concavity statement. And for that purpose, I'd like you guys to recall the expression of the Lagrangian that I showed earlier. But what I really want you guys to note is that somehow it only really depends on the second moment of these jump operators in the frequency basis. So in what precedes, I'll try to do a proof by pictures or a diagram manipulations to try to illustrate how to write this second moment itself as a convex combination and kind of use that as intuition for why that's enough. To begin, it turns out that we can write these jump operators in the frequency basis using the following picture as an expectation, that's where the moment comes in, of the jump operators, which are L local Pauli's P, conjugated by the circuit. Turns out that using linearity of expectation, this expectation over Pauli's is just a well-known swap operator. But now, recall that the circuit C is low depth. And the swap operators are supported on the light cone of some qubit. So this leads to a very convenient light cone cancellation, where the qubit in the middle, the single line, which doesn't touch any circuit, is completely decoupled or disentangled from the rest of the process. Now we can plug our identity back in and replace the swap by an expectation over Pauli's. And to conclude, we simply note that this expectation over Pauli's can be written as conditioning on the Pauli being a single qubit Pauli, and then everything else. But the single qubit Pauli is completely disentangled from the rest of the circuit, so we get another very clean light cone cancellation. Just to say the same thing in English, all we're really saying here is that the second moment can be written as a convex combination of two other second moments defined on disjoint sets of jump operators. That's the conclusion of my proof sketch. May not seem too convincing to many, but I hope it conveys the real idea of leveraging this concavity statement.
Sorry, how do you know that each individual part is also has the same fixed point?
Great. Because they're both defining Davies generators on specific families of jump operators.
Oh, they do. Oh, yeah, right.
Yeah, just to rephrase, they're both guaranteed to, via detailed balance, to converge to the Gibbs state, but we only know how to analyze the simple picture, not the other one. It's entirely plausible that the mixing process is even faster. We just don't know how to tackle the second term.
Okay, yeah, some global operations can just mix this faster than information.
Potentially.
Yeah, so here, since the coefficient for the first term is already close enough to 0, while you also require the second term, so also has a Gibbs state as a fixed point, can we just ignore the second term?
Right, so that was the claim I stated earlier, where once we have this concavity statement, I argue that the log Sobolev constant of this joint process is lower bounded by that of just one of them, because they both converge to the same fixed point.
Yeah, so my question is, what if the second term has a different fixed point? Can we just ignore it? Because
Yeah, so if it had a different fixed point, we would not be able to ignore it. But that was similar to his question, where we claim that this also has the same fixed point.
Okay, I see.
Great. So that concludes part 1, where arguably the key idea was on designing and leveraging this concavity statement.
You have the component number of recordings you're doing the
Yes. Yeah. The number of jump operators is linear in n and exponential in L, the locality. So there's 4 to the L Paulis on it.
when you implement them, you have to implement in the block including all of those.
Yes. Yeah. I'm skipping over step 2 because it arguably kind of leverages heavily Anthony some priors. But yeah, we have all the details very explicit. Yeah.
How important is it that C is unitary? I'm asking because some of these parent Hamiltonian constructions were.
It seems to be.
Right?
It seems to be very important.
That's in the last step, like the slide concept, where you cancel out things. Or?
Not only, in fact, it also appears in arguing that the Gibbs state is the output of a circuit, a noisy output of a circuit. There's this identity.
That's really the question. Like if the C's are not unitary, it's just the output of a non-unitary circuit.
That may be true, but we argued to do that we could place the unitaries in the exponent using the unitarity, and that just won't work, even if they're not unitary. Great, so moving on, part 2 is about fault tolerance and designing circuits which are hard to sample from under input noise. So arguably, the start of our approach is to start from shallow IQP circuits and then make them fault tolerant. So IQP circuits are defined by a layer of Hadamard gates, a diagonal matrix D, and another layer of Hadamard gates. And they have 2 very convenient properties for us. One of them is that they inherit the hardness of exact sampling from measurement-based quantum computation. And they're defined on a restricted, in fact, commuting gate set, which we'll use shortly, namely Z, CZ, and T gates, or if you prefer, CCZ gates. However, work by Gao et al. And the Eisert group showed that, surprisingly, there exists a family of shallow or constant depth IQP circuits, which is hard to sample from, even up to constant total variation distance, so long as we assume some average case hardness statement of computing certain partition functions. This is the key underlying conjecture we're going to need. It's like an average case hardness statement for complex valued partition functions. But at its heart, it's really just saying that there exists a shallow IQP circuit, which is hard to sample from, even approximately. Any questions? Because this is really the only complexity theory slide I need. Great. So moving on, the main result of the second part is the following lemma on the fault tolerance of shallow IQP circuits. We claim that for any fixed noise rate, we can take any IQP circuit and embed it into another non-IQP circuit, such that first, the new circuit is robust to input noise in the following quantitative sense. We can embed C into a new circuit C tilde, such that even under input noise, we can sample from C tilde and classically post-process it into a sample epsilon close to the ideal distribution of C.
Should noise rate be anything less than 1 or
Anything less than 1, because this is depolarizing noise, so it's equivalent to bit flip noise with probability less than half.
then your beta is like log 1 over 3. Yeah, something. So it should go high.
Any constant temperature, yeah.
Okay.
Keep in mind that the order of quantifiers matters here. We're fixing the noise rate first, then constructing the circuit. Great. So the second bullet point is that the depth and the locality of the circuit C tilde is only slightly increased from that of C, namely by an additive log n factor. That's where the advertised locality dependence comes from. To address Dominic's earlier question, we have a earlier version of this result where even by fine-tuning some prior work, we only got a log n factor.
So why isn't it true to the log n, the finite log n, because it's geometrically local or something?
Yes, that's a very good question. We carefully design the increase of locality to not be exponentially dependent on the depth. Great. So what do these fault-tolerant circuits look like? To begin with a very, very pictographic outline of what they look like, the starting point is really to notice that we only care about input errors. So somehow, fault tolerance is all about distilling very clean input qubits to the circuit. So to do so, we're going to design a carefully tailored gadget. And we're going to place this gadget on each of the n input qubits of the circuit. So depicted here, there's 9 logical qubits. But where this differs from standard error correction is that typically in quantum error correction, you encode 1 logical qubit into a code block, and then apply gates transversely on the entire block. Here, what we'll do is we're going to pick 1 specially designated root qubit per gadget, and just input that qubit into the code block. Great. So this is still very high level for now, but I wanted to give some foreshadowing for how we would go by doing this at low overhead. And to do so, we really just need 2 ideas. The first one is going to be a nice structural property of IQP circuits, which enables us to just focus on error detection and not error correction. And the second idea will be the design of a gadget roughly inspired by state distillation. I'll spend the next few slides discussing this idea. So to begin, I've depicted here my favorite IQP circuit. It's comprised of layers of Hadamard gates, CZ gates, and T gates. Now, suppose we knew that an error had occurred on qubits 1, 2, and 5. Then after the layer of Hadamard gates, they actually become Z errors, which are diagonal, much like the rest of the circuit. And therefore, they commute through the circuit. Subsequently, after the last Hadamard gate, out pops an X error on the same qubits 1, 2, and 5. So what this suggests is that if we knew where the errors had occurred, then we would be able to correct them in post-processing simply by subtracting them from the measured output string. Great. So with that, I can now return to the outline of the fault-tolerant circuit with a new bullet point, which essentially says that we're going to design these gadgets to be able to, by measuring the leave qubits, which are the blocks in blue, we'll be able to infer what the root qubit was, what the what the error was when we once input it into the qubit. And crucially, we're only going to focus on performing these operations and like processing this information in post-processing, somehow deferring the decoding overhead, because typically if our goal was to correct the error before it was input into the circuit, that might be very costly in terms of circuit depth and adaptivity. Great. So to briefly comment on the second idea, which are what our gadgets look like, arguably the inspiration lies in the repetition code, where suppose we were given k bits, S1 through Sk, drawn at random from the Bernoulli distribution. And then suppose we place them on this tree where the kth bit, the root, is placed at the top, and all the other ones are placed on the leaves. Then our gadget, which essentially encodes the kth bit into the repetition code, applies a CNOT gate from the root directed to all the leaves, resulting in their addition. The key observation here is that by reading off the leaves and computing their majority, we actually can recover the root bit. In particular, because S1 through Sk minus 1 are biased towards 0. Their majority. Yeah. Keep in mind that we're only doing this in post-processing. We're not doing this in a quantum circuit. Great. So when you can do something well, just do it again. And thus, we recurse this idea without getting into too much details by placing the same repetition gadget on each layer of a B tree. And I'll claim, without too many details, that this actually gives us a gadget to recover the bit at the root, where the depth and the locality is only a log n factor, which again is where the advertised log n locality bound comes from.
So that's also part of the circuit.
Yes. Yeah. So the quantum circuit itself is just a sequence of CNOT gates in this tree. And that precedes the logical block.
And then the logical block just acts on the root.
Yes. Yeah. Great. So that was the sketch of the fault tolerance claim. With that, I can conclude part 2, and where to summarize the key ideas are really just a simple error propagation and a state distillation step akin to magic state distillation. And with that, I wanted to conclude by discussing some future directions. So there are two, or I guess I can pause for questions if there are any. Great. So for future directions, we find two outstanding questions in this line of work, and which we don't really have any tangible approach to tackling. And the first one is on the BQP completeness of Gibbs sampling at constant temperatures. That is to say, can you embed any quantum computation into a high temperature Gibbs state, and simply by sampling the Gibbs state, extract the outcome of the quantum computation? Yeah. Anyway. And the second question is on quantum advantage with noisy shallow circuits. So in particular, the question is, does there exist a family of shallow quantum circuits, constant depth quantum circuits, which remains classically hard to sample from under depolarizing noise everywhere? So naturally, if you could solve this question, you would immediately lead to an improvement of our main result, but with constant locality instead of log n. In fact, we don't know how to address this question even with input noise. With that said, I can conclude with a quick advertisement on a one-day workshop next week here at the Simons Institute on quantum advantage, noisy shallow circuits, and fault tolerance to discuss some of these questions. Yes. And thank you very much.
More questions from Thiago? Yes.
Can I go back to the first question? The first open question? Yeah, I'm wondering is there any connection with quantum security Like suppose that you have a very good conductivity theorem that implies this.
That's an excellent question. So you could certainly embed the quantum computation into a high temperature Gibbs state if you had a PCP theorem. You wouldn't have the complete part in the sense that it may not be efficiently samplable. Yeah.
So BQP is like a promise class, but here you're talking about sampling. So
yeah, in principle, the idea would be to sample and then extract the information. Like the decision of the language.
So how is each jump operator in the Davies generator?
Great. The rough outline is that since our Hamiltonian is commuting and has integer spectra, there's numerous ways that you could do that. We pick the operator Fourier transform. It's just a like Hamiltonian simulation and a block encoding of the jump operators.
For finite amount of time? Or?
Yeah, it's finite because the Hamiltonian is commuting, so it really just suffices to implement like Hamiltonian simulation of local terms. Yeah, the fact that it's a commuting Hamiltonian is extremely convenient for us. Yeah.
Very nice work. And I was wondering, what happens if at the beginning of the construction you take a Hamiltonian that is not single-side interactions, but a Hamiltonian for which that is commuting again local, but then for which that the Davies generator converging to the associated Gibbs state is rapidly mixing. Does the whole construction with the light cone still follow, or?
Okay, so the short answer is if you knew what the circuit was, you could rotate your jump operators, and it would be almost equivalent. The long answer is if you don't know what the circuit is, it might be a lot more tricky, but plausible.
Can you expand on this comment on how it is hard to read off the IQP circuit from the description of the Hamiltonian?
Yeah.
Can you elaborate on why you think that is? Is there like a crypto kind of reason? Like, can you
we don't have a formal reduction. It's just this intuition that says, you're given somehow light cones or basis elements of the unitary. That's kind of all you have access to. And the question is whether you can extract a globally consistent unitary just with these local patches. And you can definitely do that in one dimension by kind of finding consistent local patches and then using dynamic programming. But in 2D, we really don't have good intuition. This is not a rigorous statement. And in fact, we don't know, we're not claiming that there does not exist any other way to produce these Gibbs states. However, what seems to be true is that however you would do it may be more expensive than linear time in n and exponential in the locality.
Okay. If no more questions, let's thank Thiago again for a great talk.